Hello everyone. In this video I'm talking about 4.4 and 4.5. This is, according to the schedule, what we were going to talk about on April 13th. So let's get into it. The mean value theorem is going to be the main thing that we study in 4.4. As a way of kind of working our way to that theorem, we're going to first talk about Rolle's theorem, which is a special case, basically, of the mean value theorem. And here's what it says. Let f be a function that satisfies these conditions. So f has to be continuous on some closed interval. And if you look at the open interval, number 2 says that f needs to be differentiable on that open interval. I'll talk about what differentiable means once we're working on an actual problem. We also need that f of a equals f of b. In other words, that the function is at the same height or output for two distinct inputs. Then there is a number. So if all those things are met, those three things, then there must be a number inside of a and b such that the derivative at that number is 0. So I'll draw a quick picture. I think, like all these theorems, if you can draw a picture to make sense of it, it helps a lot, or at least it has helped me a lot in my experience. I guess more visual in that way. So I'll draw a picture of this down here. So let's just imagine we had some continuous function from a to b. So I'll just draw a function kind of like this. So this is f. So number 1 said that f is continuous on the closed interval a to b. So I'll just make an interval now. So let's call that a, and let's call this b. So f does appear to be continuous. It's nice and smooth. There's no holes, there's no jumps. There's no kind of different pieces to this graph. It's all just continuous. So that is number 1 being satisfied, right? This is a continuous function here. Number 2, differentiable. As I said, I'll talk more specifically about this when we're talking about example 1 and other examples. But basically, differentiable means that if you think of the slopes of tangent lines, that they all kind of continuously, smoothly turn into the next tangent line. So if you take tangent lines from the right and then tangent lines from the left, they agree at all meeting points along this function. So that's number 2. I'll talk more about that in a little bit. The f of a piece. So right now, as I chose a and b, number 3 is not satisfied, right? You can see this would be about f of a right here. Up here is f of b. So I actually, to perform this rule, I need to figure out a spot where the function has the same output for different inputs. So if this is b, I would actually need a to be right here. So I'm going to shift a over a little bit. Let's call a right there. And that way, number 3 is met, right? Here's the output, f of a equals f of b, because these are at the same heights for these different inputs. So 1, 2, 3 are all met now. We have this, this, and this. So what the conclusion is, or what the result is, there must exist a number c inside of a and b such that the derivative evaluated at c is 0. And you could probably see where that c is. All right, so somewhere right about there, we would have a number c. And since the derivative would be horizontal, or at least I'm imagining it to be horizontal there, that would mean that the derivative evaluated at that number c, in other words, the slope of that tangent line, would be 0. Okay. Conceptually, if basically what goes up must come down, and if that's happening continuously, then there was a maximum point. Or what goes down must come up. If that happens in a continuous way, there must have been a minimum point. Okay, so let's look at an actual example, try to apply all these things. So it says, example 1, with this function, find all numbers c in the interval -2 to 2 that satisfy the conclusion of Rolle's theorem. Okay, so first things first, we need to make sure that these three things hold true so that we can then move to the then part. Okay, so for this function, we're going to need that it's continuous from the open interval, the closed interval -2 to 2. So let's write this down. So because we're needing to satisfy this first one, I'll go ahead and write out how this function meets it. So f is continuous on this closed interval -2 to 2 because f is a polynomial. Okay, so we have that condition met. Number 2, I'm just looking at it up there. It says f is differentiable on the open interval a to b. So f is differentiable on -2 to 2 because if you imagine f prime, the derivative of f prime is also a polynomial. So a derivative will not be, or a function, let's say, a function will not be differentiable at any locations where the derivative is not defined. Okay, so a function, if it's able to be differentiated, if you're taking a derivative of it, the function will not be differentiable at any location where the derivative is undefined. Okay, since f is a polynomial and f prime would therefore be a polynomial, f prime would not be undefined anywhere. In other words, f prime is defined everywhere. So number 2 is met. Number 3, we need that f of -2 equals f of 2. And if you try that, if you plug in -2 and 2 into the function, what you get is -6 for both. So indeed, f of a does equal f of b, right? A here is -2 and b here is 2. And I believe if you try that, if you plug in -2, use parentheses where needed, and then plug in 2, use parentheses as needed, you'll get -6. So because those three conditions are met, we know that there must be a number c inside of -2 to 2 such that f prime of c is 0. In other words, the derivative is 0 there. In other words, there's a min or a max there. Okay, so what I'll do now is take the derivative of f. So f prime of x, I'll go searching for this c now, because we're supposed to find all numbers c in this interval. Okay, so f prime of x will be 3x squared minus 4x minus 4. Right? So it turns out that this thing factors. Basically, we're looking, if you take a times c, -12, we're looking for two numbers that multiply to -12 and add up also to -4. If we can solve this puzzle, then this thing factors. So it's true that -6 times 2 is negative 12, and negative 6 plus 2 is negative 4. So what I can do is rewrite f prime. You could also use the quadratic formula, by the way. So also, what I'm doing is I'm really looking for where this derivative is 0. So I can just put that 0 there now, right? Because we're trying to find this, where this is happening. So I'm setting that derivative equal to 0 and then solving. So I now have 3x squared minus 4x minus 4. And I can now rewrite the middle term. I'm just factoring here, you guys, just so you know. Just going through this weird factoring process. So 0 equals 3x. Factor out the 3x. And then that leaves behind an x minus 2, right? I'm factoring out of these two. Then factor out a 2. So factoring now out of these two, I'm factoring by grouping. So I have x minus 2. And then this would equal, if I factor out now x minus 2, which is common to both, I get 0 equals x minus 2 times 3x plus 2. Solutions to that are going to be my c's that we're looking for. So I'll have x equals 2 as a possibility. And then if I think of this one being set to 0, I'd have x equals negative 2/3 as a solution to it. Right, so setting both of these to 0 and solving, we get these. These are those c's. And just looking back at the problem, we were to find all numbers c in this interval negative 2 to 2 that satisfy this conclusion. All right, so we have found those. These are those two numbers. So c equals 2, right? Because 2 is inside of negative 2 to 2. Here it is right here. It's inclusive. And we have let's see. So going back for a quick second. So it's potentially a little confusing. We want to find all numbers that are in this interval, but the theorem states that the existence is only in the open interval. So we actually cannot include this 2. This 2 cannot be included, right? The theorem states then there is a number in a to b such that this is happening. So since 2 is not a member of negative 2 to 2, then we can't use 2 as one of our answers. Negative 2/3 is a member of negative 2 to 2. Okay, so that C, I'll write it up here, kind of running out of room. That is the only answer that we have, this negative 2/3. So just to summarize, although that 2 is in this interval, the theorem cannot say anything about B, right? There is a number in A to B such that this happens, right? So we're really working with the interval of negative 2 to 2, not inclusive. So I can't include 2 in my answers. Okay, so just the negative 2/3 works. All right, so the next one I'll do is example 2. We need to talk about now the mean value theorem, which is just a more general case, really, of the theorem that we just saw, Rolle's theorem. Let's read it, and then I'll try to draw another picture that will hopefully make more sense of it. The mean value theorem. Let f be a function that satisfies the following conditions. So f needs to be continuous on the closed interval, differentiable on the open interval, that's all the same. And then this exists. Basically, the derivative evaluated at a number would equal the average over the interval a to b. Right? This is the average rate of change. And what this is saying is that there's some exact point c such that the instantaneous rate of change would equal the average rate of change. Let's draw a picture. So I'll just try to draw some fairly general graph here. Let's say we have this, and let's say that this here is A, this here is B. That would mean that if I take this imaginary line, the slope of that line would be exactly this right here, this right side. Right, so that slope would equal the function evaluated at B, this is our function by the way, minus the function evaluated at A, right? The difference in the heights over the difference in the x's, right? This is the slope formula. On the left, what the claim is that there must be a c inside of A to B such that this average rate of change is exactly equal to the instantaneous rate of change at that number c. So I'm doing my best to imagine that location. If you imagine this line, this would be the instantaneous rate of change. In other words, that would be a tangent line to the curve. This would be that location C if this line and that line have the exact same slope. So this would be C. Right, here's f of A. Here's f of B, just to fill in everything. And this was our function f. I don't want to confuse things. This is our function f here. The value of this slope would be f prime of c. And here is this line and that line being parallel. In other words, this thing would equal this thing. And that's exactly what this whole thing is saying. Conceptually, because even with the picture, maybe you're like, yeah, what? Imagine you're driving a car, okay? You drive, maybe this is your position from your house, okay? So you start driving somewhere, and then you slow down, and then you get there, right? So let's say you start driving, you're going away from your house, and then you eventually stop and you get to your destination. So if you, let's say you started with some speed, you ended with 0 speed. So if you went to, let's say, LA from San Diego, and sometime you're driving 20 miles per hour, sometimes you're driving 0 miles per hour, sometimes you're driving 75 miles per hour maybe. When you get to your destination, you will have averaged some speed, right? So this is your average. Let's imagine this is your average speed. So if you went 20 sometimes, you went 75 sometimes, maybe your average speed was, let's say, 45 miles per hour. So this might be that 45 miles per hour. What this theorem is saying is that if this is happening continuously, so if you are averaging 45 miles per hour for some continuous trip, there must have been at least one exact moment where you were going exactly 45. So if your average is some number, right, some average of a function is some number, this is the average, then there must be some number in between that interval such that the average is exactly equal to the instantaneous. So if I'm driving from here to LA and my average speed was 45 miles per hour, there must have been at least one moment in time when I was going exactly 45 miles per hour. That's what this theorem is saying. Okay. So applying that. So example 2, it says with the function find all numbers c in 0 to 2 that satisfy this MVT, the mean value theorem in other words. So I'll write down some of the necessary things. So for number 1, we need that f is continuous. So f is continuous on this interval 0 to 2, right? I'm basically going through these two things here. Because, you can probably answer that, but because f is a polynomial again. Okay. Number 2, we need that it's differentiable on the open interval 0 to 2. F is differentiable on the open interval 0 to 2 because f prime would also be a polynomial. If you imagine f prime, so that won't be undefined anywhere, in other words. So it will be differentiable everywhere. So what the theorem says is that then there would be a number c inside of 0 to 2 such that the instantaneous rate of change of the function exactly at c is equivalent to the average rate of change of the function from the interval 0 to 2. Okay, so let's set this up. So there must be a c in 0 to 2 such that f prime of c equals f of 2 minus f of 0 over 2 minus 0. Where the heck did that come from? That's exactly what is here. Right, so if these two requirements are met, then we can go to this conclusion and find that number c. So what I'll do on the left is I will take the derivative and then evaluate that derivative at c. And then over here I'll have some number, some average rate of change of the function. So f prime of c, I'll go ahead and take the derivative. So I'd have 3x squared, so I'll have 3c squared. Right, I'm taking the derivative and simultaneously evaluating that derivative at c. And then I'll have minus 1, just again taking the derivative. On the right, this should be equal to, now I'll take 2 and I'll plug that into the function. So I have 2 cubed minus 2, right? That's the function evaluated at 2. In other words, f of 2, this part. Sorry about that. So I have 2 cubed minus 2, and then I'll have minus 0 cubed minus 0, right? Plugging in the 0 now to the function. This is all over 2. Right, 2 minus 0. So now what I'm solving is this equation. So I'll have 3c squared minus 1 equals, after some simplifying, you'll see that this number is 3, right? You have 8 minus 2, which is 6. 6 over 2 is 3. So I'm solving this equation for c, and that c will be the c that the theorem is mentioning. So add 1, solve for c. 3c squared equals 4, divide by 3, so on. C squared equals 4/3. Square root, so c equals plus and minus the square root of 4/3 You can write that as 2 over root 3 if you want, plus and minus 2 over root 3. The only thing is that one of these numbers is not in our interval, and we were just looking for the numbers in 0 to 2. Okay, so we're only going to take the positive case, right? 2 over root 3, if you check that on your calculator. Let me just do that real quick. 2 divided by root 3 is 1.15 about. So that does fall in this interval here, this 0 to 2. But I'm going to write it in exact form. So I'm throwing out the negative, and we'd have c equals just 2 over root 3. I don't care if you rationalize that. Okay. All right. So with that, I'm going to leave example 3 open. So on page 64, you'll go ahead and work on that one. Of course, I'll attach the solutions to all these alongside the video. So on to 4.5. So derivatives and how they help us think of graphs, basically. So as we've seen, derivatives are kind of our access into slopes of tangent lines. Slopes of tangent lines would tell us how a function is evolving over its domain, right? We can know whether a function is increasing, whether it has a positive slope. We can tell whether a function is decreasing because of its negative slope. We can tell when a function is constant because it would have 0 slope. So we learn a lot about what a function is doing through derivative. There are a couple tests. Here's the increasing/decreasing test, basically what I just said. If the derivative is positive, then that function's increasing. You have positively evolving tangent lines in that interval. If the derivative is negative, then you have decrease on that interval. The first derivative test is an important one. So this will be like our sign chart. So if f prime, the derivative, changes from positive to negative, that picture would look like this. You'd have positive, 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 negative, 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 right? If that's happening, then there's a maximum. If the derivative changes from negative, here's negative, negative, negative tangent lines, right? Imagine the slopes of tangent lines to here. Negative, 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 and then switches to positive. This would be a minimum. Okay, if f prime is positive to the left of c or negative to the left and right of c, basically for this last picture, you would have maybe positive, 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 0, and then more positive, positive, positive. Or you would have negative, 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 0, and then negative, negative, negative. So this would be negative, positive. If that's the case, then there is no min or max. And you can kind of see that with these clumsy pictures that I drew. All right, let's try one. So it says, find the local minimum and maximum values of the function. Okay, so derivative. This is definitely the job for derivative. So I will take the derivative. So f prime of x will have, let's see, 12x cubed minus 12x squared minus 24x, and then we get a 0. Factoring, as I was saying while we were meeting in person, factoring is a skill you want to maintain or develop or improve because it's going to help us find these local mins and maxes quite a bit. We're going to be eventually setting this derivative equal to 0. And from the 0 product property, we know that if we have a bunch of factors equal to 0, then those are easy to solve, right? That 0 product property says if you have factors multiplying to 0, then at least one or both of those factors needs to be 0 to do that. So 0 product property. For that reason, I'm thinking factor here. So it looks like a 12x can be factored out, leaving a x squared minus x minus 2. Noticing that this factors also. So f prime of x, still just the derivative. We have 12x, and then it looks like if I have x minus 2 and x plus 1, then we have a good factorization of x squared minus x minus 2. Okay, now to find the critical numbers. So I'll set the derivative equal to 0. We'll have 12x, x minus 2, x plus 1. So we're getting that 0 needs to equal 12x, or 0 needs to equal x minus 2, or 0 needs to equal x plus 1. So x equals 0, x equals 2, x equals negative 1. These are our critical numbers. These critical numbers now go on your sign chart. So over here, I'll kind of draw this number line. On that number line, I'll place these numbers here. So negative 1, 0, and 2. And now what we're doing is we're testing. This is, by the way, a sign chart for the derivative. So what I'll do is I'll test in between each of these to learn what's happening in those intervals. So I'll test at, let's say, negative 2, negative 0.5, 1, and 3. So I'll call these my tests to see what the slopes are doing there. So these are just the tests. So the spots with the x's are just the tests. These dashed ones are actually critical numbers. All right, so what I'm now doing is I'm taking these tests and I'm placing them into the derivative. So I'm going f prime of negative 2 and looking for the sign. I actually don't even care what exact value it is. I just care about the sign of it. So I'll have, if you think about negative 2 going into the derivative, I'd have a negative number times a negative number, right? I'm plugging in a negative 2 everywhere there's an x. So this would be negative 24, this would be negative 4, so negative times negative is a positive. And then here I'd have negative 1, so this is back to negative. It's actually exactly negative 96, if you check that. So negative 96 is less than 0. Which means throughout this interval, I have negatively sloped tangent lines. What happens exactly at negative 1? I get a 0 for the tangent line there. F prime of 0.5, that's my next test. If you plug that in to the derivative, check my work, but I got 15 halves. Which is greater than 0. It's a positive number. That's actually all I care about. So that means that it's a positively sloped tangent line throughout that interval. Test at 1, f prime of 1. Plug that in, you get negative 24, I believe. That's less than 0, so I have negatively sloped throughout that region. I then have another critical number, so I need to check at 3, f prime of 3. I'm taking all these and plugging them into the derivative, right? These are all primes. If you plug in a 3 to the derivative, you get, I believe, 144, which is greater than 0, so I have all these positively sloped tangent lines throughout that. So thinking about this now, these are a description of tangent lines. So I would have negatively sloped on the left, and then right at negative 1 I have 0, and then I would have positively sloped on the right. So it looks like a minimum is occurring right there. And then here I would have positively sloped on the left because of the pluses. I would have exactly 0 slope at 0, and then I would have negatively sloped. So it looks like I'm getting a maximum there. And then here it's going from negative to positive. So just to draw that hypothetical picture, it's negatively sloped tangent lines on the left. It's exactly 0 at 2, and then it's positive on the right. So I have a minimum there. So it looks like a min, a max, and a min. So I have 2 local mins. So the local mins, now to find the actual minimum value, we're now going back to the function, right? To actually see what the output is there, to actually see what the minimum or maximum is, we don't go to the derivative anymore. We go here to the function. So f of -1, right? That's f, not f prime. If you plug in a -1 here, I believe you get 0. That would be our first minimum. F of 2, that corresponds to our other minimum. F of 2 would be -27. And then for the max, we just have one of them. So I have f of 0 equals 5. That's all we were being asked to do there. Although that was a lot. Okay. I'm leaving example 5 open for you guys, but let's talk about concavity real quick, and then we'll go on to number 6. So concavity basically is a description of whether a function is increasing or decreasing as far as its derivative. Not its function values, but its derivative. So the rate of change of the rate of change, in other words. We'll do this next problem. I think it'll help a little bit. But basically, just to draw a quick picture, let me grab a piece of paper. Computer almost fell. There we go. Okay. So looking at this concavity test statement, let's draw a quick hypothetical graph. So check out this part of the graph specifically. So there's a portion at which for sure it's increasing, right? It's even increasing all the way throughout this location, right? But the rate of increase is larger here. So if you think about our current situation, like the number of COVID-19 deaths or the number of COVID-19 cases, we're kind of in a place where there are still more and more cases being added, but the rate at which those cases are being added is starting a little bit, at least locally, to decrease. Even though there's still more people getting sick, the amount of people per day that are getting sick, from what I've heard, is starting to slow. So what you would have is at some point here, there would be an inflection. And you may have heard of people in the news talking about we're at an inflection point. Basically what that means is where a function was increasing at its highest level, now the function maxed out the rate of increase, and now it begins to slow. Even though it's still increasing, the rate of increase is lessening. So it's kind of a challenging thing to wrap your mind around, because we're now talking about the rate of change of the rate of change. Right, so all throughout this region, still more people are being added to the category, whatever we're talking about, whether it's people dying or just people getting the disease. So they're still being added to, but the amount per day would be lessening if this were our graph. So throughout this region, we would have up to another inflection point, we would have concave down throughout this whole region here. Over here, and there would be another inflection point here, I would have concave up because of this nature here until another inflection point, and then it looks like I have concave down again. Over here, I would have more concave up. So anytime we have concave up, this would be F double prime is positive. Anytime we have concave down, we would have F double prime is negative. And anytime we have an inflection point, we would have F double prime equals 0. Okay. So for the second derivative, this concavity test, the second derivative, when we set it to 0, we're not finding mins and maxes of the function. We're finding mins and maxes of the derivative of the function. Right? We have this new function, f prime, and if we take its derivative, we're now looking for a min and max of the derivative, which means when was the thing changing the fastest? Positively, or when was the thing changing the fastest negatively? I'll try to explain this more as we go on. Let's look at an actual problem here, number 6. And then I'm going to leave examples 7 and 8 open, but of course I'll post a document of solutions alongside the video. Here's the official definition of inflection point. Go ahead and read it for yourself, but I'm just going to get into this problem. So it says for this function, find the intervals of increase or decrease. That is first derivative stuff. And then it says find the local min and max values. That's still first derivative stuff. Then it says find the intervals of concavity. That is second derivative stuff and inflection points. And then use the information from parts 1 through 3 to sketch the graph. All right, so part 1 first. Okay, so find the intervals of increase or decrease. The derivative, that's its job, right? The slopes of tangent lines, whether they're positive or negative, is how we learn whether a function is increasing or decreasing. So f prime of x equals 36 plus 6x minus 6x squared. All right, simple power rule derivative there. Now we need to actually set it to 0 and solve. Right, so it looks like we have a factorization that we can do. So 0 equals 6. So this would be 6 factored out front, leaving behind a 6 plus x minus x squared. You can divide out the 6. So you can just say 0 equals, and then I'll maybe rearrange, negative x squared plus x plus 6. You can divide out a negative even if you want. You don't need to, but you can divide out a negative. So you can say 0 equals positive x squared minus x minus 6. Factoring it, so 0 would equal x minus 3, x plus 2. That would be a good factorization of this one. Sorry, I keep having an itch on my foot. All right, so the CNs, the critical numbers. If you set each of these equal to 0, you get x equals 3, x equals negative 2 as your critical numbers. Place those critical numbers on a number line. So here's -2, here's 3. So I'll use these tests. I'll test at 0, that's kind of a nice place. I'll test maybe at 5, and then I'll test maybe at -3. So these are just my tests. So I'll just make that clear. These are not defining the endpoints of the interval, they're in the interval. Okay. So now actually plugging those into the first derivative. So we have f prime of -3. This equals, if you do the math, again, I'm plugging -3 into the derivative. One quick second, I'll be right back. Someone's at the door. Sorry about this. Pause, fast forward. I'll be right back. Sorry about that. There's no pause button on this iPhone recorder. Okay, plugging in -3 into the derivative. So I'm taking these values and testing the derivative, saying, okay, derivative, are you positive or negative there? In other words, is this function increasing or decreasing there, or neither? So -3, if you plug that in, saving some time, you get -36, that is less than 0. So you have negative throughout. Okay, f prime of 0. Plug in a 0. Again, I'm plugging that into here. So get a 36 out of that. That is greater than 0. So I have positive throughout that section. And then over here at 5, f prime of 5, we have -84, I believe. You could check me on that. I'm plugging 5 in to the derivative, f prime. That is less than 0, So I will have negative throughout that section. So just to, again, this has all been f prime. So we'd have negative, 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 0, positive. So I'm getting a minimum right there. I have positive, 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 and then negative. So I'm getting a maximum right there. Okay, so to state this, I'll have increase. So we're finding the intervals of increase. Keep that in mind. So I would have that we'd have an increase from negative infinity all the way up to -2. Sorry, I'm reading the wrong one. So increase, I'm looking at positive. So I'll have increase from -2 up to 3. Sorry, I'm just checking one thing here. Okay, cool. So from -2 to 3, we'd have increase. By the way, you can go to Desmos and plot this and just check that all this is matching up. Decrease. So now I'm looking at any negative interval, right? Whenever the derivative is negative, that's a section of decreasing. So I'll have from negative infinity up to -2, not including either, union 3 positive infinity. So that's part 1. Okay. Part 2 says find the local minimum and maximum values. We kind of have done a lot of that work already, right? So this sign chart is saying, hey, there's a minimum here over at -2. There's a maximum over here at x equals 3. To actually find the min and max are the outputs. Okay, so the min of a function is an output. The max of a function is an output. We know the horizontal locations, the inputs for which those min and max occur, but to actually find the value, we take those numbers and plug them into the original function. Okay, so we'll have a local max, according to our sign chart, right here at 3. So I'll have f of 3, and that would equal, if you check that, I'm plugging in 3 here, I believe you get an 81. A local min, if you plug our -2 in, again from the sign chart, so f of -2, plug that in, and we get a -44. And that would be our local min and max values for part 2. Okay, so part 3 says find the intervals of concavity. So for concavity, we're now talking about the second derivative. Okay, so we'll have f double prime. So now I'm taking the derivative of the derivative. So I'm looking here and taking that derivative. So I'm getting 6 minus 12x. Set it to 0, basically find the critical numbers of the second derivative and solve. So solving that, I'm getting x equals 1/2. So now I do a sign chart for the second derivative to figure out concavity. I'm placing 1/2 on that sign chart. I'll test at 0 and 1. Let me make my x. All right, so this is, by the way, f double prime, so I'm going to test f double prime at 0 to see what the concavity is doing there. So I'm taking now 0, plugging it into f double prime. It looks like I get 6, which is greater than 0, so I have a positive interval. Then checking over here at 1, f double prime of 1, it looks like plugging in a 1 for x, I'd get -6, which is less than 0. And then I will notate that here on the sign chart. So there is a inflection point here at 1/2, in other words. And what I'm seeing here is that we're concave down, right? Negative means concave down, and we're concave up throughout this region. This is concave up, this is concave down. So here we are, we have concave up, here. So from -infinity to 1/2, right? Any positive region means concave up. Concave down, any negative region is concave down, so I have from 1/2 to infinity. Okay. Part 3 also wants the inflection points. Here we just have one inflection point. So inflection point. So it's going to occur here at 1/2. But then to actually find the output, right, the actual location of the inflection point, just going back to this, I need to evaluate the function, right, to figure out where the height is. I know that it's occurring at 1/2, but I don't yet know what the height of that inflection point is. So I'll have f of 1/2. So plug in 1/2 to the original function way up here. And I believe what you get out is 37/2. So the inflection point is a point. So we would have 1/2 and 37/2. So this is my part 3. All right, so a quick graph, a very quick graph. I'm using this space here. So for part 4, here's a quick sketch, right? That's the key word here. So we'll have something that looks like this. It's a cubic. We're decreasing, right, from infinity to -2. So I'm looking here, there's a bunch of decrease from -infinity to -2. So I'll go like this. There's my decrease, here's -2. Then it increases. There's an inflection point, and then it has a max, and then it goes down again. So this would be the inflection point. This would be our min at -2, -44. This would be our max, which was happening at 5. Sorry, at 3. And the output is 81. And I think that's all the necessary information. Okay. So kind of a lot, I realize. Please work on the remainder. I'm leaving 7 and 8 undone, but I'll of course attach a document with the solutions next to the video. All right, talk to you next time.